Hello, and welcome to Aggressive Physics. Today is day 125, and what I'd like to do today is discuss magnetism. Now, first of all, there's a very close relationship between magnetism and electricity. In fact, if you have a moving magnet, you can create electricity. And if you have a moving charge, such as an electron, you create a magnetic field. So electricity and magnetism are often taught together. Now what we did is we discussed static electricity first, which is stored charges. Then we discussed current electricity, which is moving charges. And now we're going to discuss magnetism. Now the moving charges create magnetic fields. And we're going to have ways to determine the direction of the magnetic field and the strength of the magnetic field based on the motion of the electrons. When you start your discussion of magnetism, though, it's typical to start with permanent magnets or temporary magnets, which are magnets that maintain their magnetic properties. Originally, magnetism was discovered because certain minerals have magnetic properties. In fact, they are the original permanent magnets. Lodestones are magnets that exist naturally in the Earth's crust. Now, what we need to remember about magnetism is what we probably learned as little kids playing with refrigerator magnets or playing with magnets back in elementary school. And that's the fact that a magnet has a north and a south pole. And just like charges that had positive and negatives, the north and south poles react similarly. In fact, like poles repel and unlike poles attract. So if you have magnets that you would play with as a child, you probably experienced the fact that if you had a magnet, it could push another magnet away. That meant that you had the same pole. And in some instances, they would attract and be pulled together. That would be unlike poles. So when a north and a south pole come near one another, they attract. When a north and a north pole or a south and a south pole come near each other, they repel. And that repulsion is an experience of force. So the force can literally push the magnets apart or pull the magnets together. When we have magnets, you can break them. And in the course of your childhood, I'm sure at some point you broke a magnet in half, accidentally or possibly on purpose. When you break a magnet, what happens is you create two magnets. You have a north and a south pole on each. So if you break a bar magnet in half, where you had a north and a south pole of the bar magnet, when you break it, the north pole stays on the same side, and now you have a new south pole which is closer, and the south pole stays on the same side, but where you broke it, you have a north pole. If you keep breaking magnets smaller and smaller in terms of their pieces, you'll find that you can never have a situation where there's only a north or only a south pole. There are no monopoles that exist with magnets. You always have to have a north and a south pole. Now, the Earth itself acts as one big bar magnet. And you have the magnet that, if you can visualize it, exists vertically through the north and the south pole of the Earth, and it's stuck in the middle of the spheroid. Now, we talk about the north and south pole geographically. Now, North Pole, which is near the top of most globes, versus the South Pole, which is near the bottom of most globes when they're mounted, will be geographic north and south. However, magnetic north and south are actually the opposite. The South Pole of the bar magnet exists near the North Pole geographically, and the North Pole of the bar magnet exists near the South Pole geographically. They are not exactly at the same point as the geographic north and south poles, and we call that magnetic declination. Now, the way this works is the South Pole of the magnet exists near the North Pole geographically. So when you use a compass, the North Pole points towards geographic north, which is magnetic south. Now, south and north on the Earth have actually switched a number of times. It's not something that is a constant. In fact, the location of true north and true south has changed over the years. every 200,000 years or so, the poles of the Earth's magnetic fields actually switch. And that is a process that occurs over the course of many years. But we can tell that from the plate tectonics, where the plates are separating. We can see that the new rock that's created will line up within the Earth's magnetic field. And since we know the rate at which the plates have separated, that's where we come up with the approximate 200,000 year time frame for the Earth's magnetic poles switching. The process, like I said, takes thousands of years to occur, but it can be something that affects migration. It can affect navigation for us if we use magnetic fields to navigate. When you are in the woods and you're trying to figure out where you are using a compass, you are using the south pole of the magnet to do so. The north pole of the compass, which is effectively a tiny bar magnet that is suspended in usually a liquid or just suspended on a movable pivot, will point towards magnetic south, and it lines up within the Earth's magnetic field. Now, the Earth's magnetic field has a strength of approximately 5 times 10 to the negative 5 Tesla. And although the Earth's magnetic field is fairly weak, it can still orient a compass to help navigate. Now, the way magnets work is they have inside of a magnet, you have what we know as magnetic domains. And these domains are areas where the magnetic fields line up. If you have an object that's non-magnetic, what will happen is it will have all of its magnetic domains scattered. A magnet that has natural magnetic properties, all the magnetic domains are lined up. You can actually strengthen the magnetic domains of certain materials by putting them within a really strong magnetic field. In fact, you could even magnetize a paperclip or something like that that does not have naturally magnetic properties by placing it near a very strong magnet. And when you do so, it lines up the magnetic domains within the paperclip and it produces a temporary magnet. And what we have are two different types of magnets typically. We have temporary magnets that do not maintain their magnetic properties for long periods of time, and we have permanent magnets that do. Permanent magnets maintain that field strength even after being removed from that magnetic field. And typically steel is a pretty good permanent magnet. It maintains its magnetic properties over long periods of time. I have a few steel magnets in my lab that, although have been weakened over the years, still maintain their magnetic properties. On the other hand, temporary magnets lose their magnetic properties quickly after being removed from the field. The paperclip will not maintain its magnetic properties unless you remagnetize it. Other examples are iron magnets. I have a number of iron magnets that we purchased over the years that I have to constantly remagnetize by putting them in a very strong magnetic field, and then it will maintain its strength for the duration usually of a lab. Every year, though, I have to remagnetize. So iron or paper clips. You could even magnetize objects that have no natural magnetic properties if you have a strong enough field. In fact, there have been instances where small insects, such as grasshoppers, have been magnetized by being placed in a really strong field. You could magnetize a piece of fruit like a strawberry or a cherry tomato, a vegetable, by placing it in a very strong magnetic field as well. You can even magnetize, if you had a strong enough field, just about anything. Now, of course, when you remove that object from the magnetic field, you are going to lose that magnetic property. So, in conclusion for today, magnets have north and south poles. You can't have a magnetic field or a magnet itself without a north and a south. If you break a magnet, you create two magnets that each have north and south poles. You can magnetize an object by placing it within a very strong magnetic field. In fact, I have some file cabinets in my office that have become magnetized because the Earth's magnetic field has created a magnetic property for those file cabinets. Now, if I were to move them, that would reduce the magnetic field strength. If you have a metal fence at your house and you take a compass and place it near the top of the post and then again at the bottom of the post, you should see that the magnetic field changes from the top and the bottom of the post. And that's because being within the Earth's magnetic field for such a long time, the fence itself actually becomes magnetized. Of course, if you place a plastic fence, it's not going to have the same properties. It has to be a metal fence. But we have temporary magnets that only retain their magnetic properties over short periods of time, and we have permanent magnets that do. The reason we have magnets in the first place is because the magnetic domains are all aligned, and when they align microscopically, they become magnetic, and you can experience magnetic properties with those materials. So the beginning of our magnets discussion is quite brief, but it will allow us to move into more complex topics with magnetism as we move further. Thank you. All right, now the lecture today was about magnets, and what I'd like to do is talk a little bit about more applications of magnets and the different types. Now you notice I have a magnet here that's a north and a south pole. If we take that magnet and we were to separate it, chop it right down the middle, then what we'd end up having is two magnets, each with a north and a south. So you'd have a north-south there, a north and a south there. So you can't break a magnet to get a single pole by itself. You're always going to have two poles, a north and a south. So no matter how many times you break a magnet, you're still going to end up with a north and a south pole. Now inside of the magnet, we have what we call domains. And in a normal piece of metal, the domains, and this is not how it actually looks, but as an analogy, the domains would be all scattered. So we have these little magnetic regions that are all scattered. And the way magnets work is we have electrons that are orbiting the nucleus inside of this metal. Well, because the electrons are moving, if you have moving charges, then what it does is it creates magnetism. So a moving charge will create a magnet. Now, you may be thinking these are stationary. It's not moving, it's just a piece of metal. But internally, the electrons are constantly moving. So as long as we have a piece of metal, we have these domains, and it's making a number of magnets within the metal. Now, if the domains are all haphazard, it's not going to be magnetic. It's not going to show the magnetic properties because the north and south of these mini domains don't line up. Well, if we have a magnet, what happens is you have your domains and they're all aligned. And once again, this is not actually how it looks, but as an analogy, these are all lined up, so then they form a stronger magnet because they're all aligned. Now, another thing to note is that north and south attract. North and north, south and south, they're going to repel. So we have like charges, or I'm sorry, like poles are going to repel, and unlike poles are going to attract. That's similar to electricity as well, where you have the proton and the electron attracting. Two protons or two electrons are going to repel one another. So because magnetism and electricity are interconnected or intertwined, you have very similar properties. But instead of calling the north and the south a charge, we call it a pole. So we have the north pole and we have the south pole. And generally, the domains, which I mentioned before, will line up. This would be a magnet. This would be non-magnetic. But we can force the domains to line up in certain materials. Now, some materials are more receptive to lining up. And if we have a piece of steel or iron, we can line up the domains and form what we call a permanent magnet. And that will maintain its magnetic properties for longer. Now, if I were to take a second magnet that has the same structure as this one on the table, all my magnets are sticking together here, I could take the South Pole and actually repel it with the other South Pole. If I were to take the North Pole, I could repel the North Pole. Now, you've probably done this before with maybe kitchen magnets where you put it on the refrigerator. Now, if I were to bring the North and South closer, they're going to attract. So North and South attract, South and South repel, North and North repel. Oh, there's a good repulsion. And then North and South are going to attract. Now, we have different types of magnets. Those would be permanent magnets. This is actually what we call a cow magnet. And a cow magnet is something that we can put into a cow, and it'll go through their digestive system and come out the other end. And what this will do is we'll take any pieces of iron filings that may be in the grass or pieces of metal that the cow may ingest and allow it to stick to that, similar to the paper clips here would stick to that. And obviously, we're hoping the cows wouldn't eat something that large. It might be smaller, but in some cases, they may pick up pieces of metal that are bigger, and that will damage their internal organs. So as this moves through the digestive system, all these pieces of metal will be attracted to the magnet, pass through the system, and then when it's removed, when the cow goes to the bathroom, what will happen is all those metal pieces will be removed from the cow's internal organs and protect it from getting damaged. So it'll protect the cow. But they will use these to help cows with their digestion. Now, this also has north and south poles. You'll see that it's attracted here and it's repelled there. So we have repulsion and we have attraction depending upon the pole. And obviously, if I don't have it labeled like I do with this magnet, when I bring it close, this end is going to be a south pole of the cow magnet. And if I bring the south pole near it, it's going to roll away. So we have this repulsion, and that repulsion applies a force. All right, now we have a compass here, and the compass is a mini magnet that is on a pivot. And sometimes the pivot is in a liquid to make it easier to spin because it'll have less friction. In this case, it's just air. And what we'll notice is that it points in the direction of the North Pole. So in this case, we have the compass, and it's a circle in this case, and it's lined up so that the red is in this direction and the silver, and some compasses are red and white. In this case, it's red and silver. And what this is going to do is line up to the North Pole of the Earth. Now, we just used our magnet before that has the north and souths labeled. And what I want to point out is that this is the North Pole of a magnet. So if I bring the south nearby, it's going to be attracted to it. So this is the South Pole of a magnet. If I were to bring the North Pole, it will repel. So when we're using compasses, what it's doing is it's pointing towards the North Pole of the Earth. So here's the North Pole. Here's the South Pole. And if the red is lining up, and obviously not to scale, but if this is the red line here, and we just established that this red is actually a North Pole of a magnet, then what that means is that the Earth is actually set up so the South Pole magnetically is near the North Pole of the Earth. And what happens is when you have this aligned, the compass is lining up to the Earth's magnetic field. Now, the Earth's magnetic field is approximately 5 times 10 to the negative 5 Teslas. So as long as there's no other magnets nearby, it'll line up. But as soon as I bring it near a stronger magnet, in this case our magnet is much stronger, it's going to line up within that field instead. So a lot of people think that we're looking at the North Pole of a magnet when we line up our compass when we navigate. But the reality is it's the South Pole of a magnet that's located near the North Pole geographically. So the North Pole geo is actually a South Pole of the magnet. Now, what's even stranger is that the Earth's magnetic field over the years switches. And it's not constant. It constantly switches, and it's not a very quick process. It takes about 200,000 years to flip. But what that does is it'll affect navigation, it could affect migration, and it could affect other animals that use magnetic fields to help orient themselves to the Earth's location, their location on the Earth. Birds don't have GPS devices. It's an internal, innate ability. So as this switches, that may mess up migration patterns. Now, another thing to note is that we have to worry about the fact that there is magnetic declination. The North Pole and South Pole geographically are not actually lined up exactly with the magnetic north and south, and this will fluctuate. And depending upon where you are, you have to adjust a number of degrees to adjust to the shift, the number of degrees here that the South Pole of the magnetic field is shifted over, and it's changed over the years. It oscillates a little bit like this, and then ultimately, eventually, it'll be actually flipped like that. Like I said, it doesn't happen overnight, but it is something to keep in mind. When you're using a compass, you're actually using the North Pole of the compass, which in this case is the red line. Oh, let's switch it back. And it is lining up with the South Pole magnetically. So that may be something you didn't know before.